Surface integrals.
Surface integrals.
So last time we did line integrals. I was integrating along a path. Now we look at surface integrals. Integrating along a surface. So we have a parameterized surface S with parameterization G that is continuously differentiable, one-to-one, and regular, except possibly on the boundary of D. Then the surface integral is that form, the double integral along S of f ds. ds is the differential of surface area. Furthermore, to calculate this, it's the double integral over D. F evaluated along G times the norm of N dA, where N is a vector normal to the surface S, is found by G sub U cross G sub V, or G sub V cross G sub U. The order actually doesn't matter because you're going to determine the direction based on the parameterization of S, on the orientation of S. Here it actually doesn't matter, right? Because when you take its norm, you get one value. But orientation will matter later. For a scalar function. You taking E and M?
No, not yet.
Damn it. Well, the nightmare is going to start now. Are you familiar with flux?
Yes.
Oh, good. Surface integral of a vector field, more commonly called flux. Flux is a flow rate. Net flow of a field through a surface. Generally speaking, it's a force field. However, you can also have velocity fields. Right, so what's the flow rate through a certain section of pipe? That would be a flux. Two most common types of flux, electric flux and magnetic flux. So there's your flux integral. Furthermore, this is how we would evaluate it. Flux is typically represented with the capital Greek letter phi. My least favorite letter in the Greek alphabet because of flux.
What's your favorite?
Told you what my favorite was.
Psi.
Del?
Del's not a Greek letter.
I don't know.
It's just a symbol. And it's not Del, it's Nabla. I'm thinking that's what you're referring to, the Del
Yes,
operator.
Right.
Del is the partial symbol.
My bad.
Capital Psi, do you remember why?
Oh man. No, I just thought it looked cool too.
The Heisenberg's uncertainty,
Okay, yeah.
Schrodinger's equation
Okay. And it does look
from
cool.
quantum mechanics.
Okay. The pitchfork.
Well, that's lowercase.
Okay, right.
Capital Psi is the same except, again, with phi, it's an I.
Yeah.
It's an I that's going through
And
instead.
it has like the curl out, right? It has like the points that curl out on either side of the stick. No, that's not the capital Psi. No. Okay.
Well, I guess if you want to say it, kind of looks like it curls out. I don't really consider that curling, though.
Well, yeah, it probably doesn't meet the criteria for real curl.
It's literally just a lowercase I with
Very pretty.
bar, the capital I symbols. That's all.
Yeah,
It's the
that's-
exact same thing.
The serifs, I think. Yeah.
I should name it pitchfork.
Hmm?
The big pitchfork and the mini pitchfork.
Yeah.
My friend called it the devil's pitchfork because of quantum mechanics.
I don't think either have a long enough handle to really be a pitchfork. It's more like a candelabra.
It's a trident.
Again, it's not
Don't
like-
candelabras have more?
Yeah, I mean, they can just have three. Just be a small candelabra.
Is that not then not a candelabra by definition?
Why would that?
I thought a candelabra had to have a specific number of holders.
No, that's a menorah.
Oh, okay.
Yeah.
That's possible.
Menorah has 9.
So might as well do some surface angles. So again, you could be lucky enough to get the parameterization given to you. More often than not, it is not given. The lecture video does give several parameterizations. Gives cylinder, gives a sphere. It gives a plane indirectly. It gives parameterization for a surface of the form z equals g of xy. So here we're given cylindrical surface y squared plus z squared is equal to 4. Where z is greater than or equal to 0, and x is between 1 and 4. So z is non-negative, that's nice. In this case, we can write z as a function of x and y. Here's our parameterization then. also need a domain. Well, they told us X already. What about Y?
Is it 0 to square root of 2?
Yeah, but I think I'm not gonna say it. I'm gonna answer that question. How do we get G?
This one's given to you in the lecture video.
Oh.
Because it's of the form z equals g of xy. It's just xy, g of xy.
Okay.
That's your parameterization. That's one of those predefined ones.
Negative 2 to 2.
It's negative 2 to 2. The norm of n also already been derived. Again, refer to the video. I'm not rehashing it. Look at g of xy, which is z. What is its partial with respect to x?
Zero.
0. Partial with respect to y?
-2y times square root of 4 minus y squared.
Square it.
Oh,
This simplifies. Evaluate the integrand along G. Well, that's easy. What should Z be replaced with?
4 minus y squared.
Times norm of the normal vector, dA. What order do we want to do? dx dy or dy dx?
first I looked at dy dx.
Well, actually, write this first. What does the integrand become?
1.
What does that integral represent?
Top bound minus bottom bound.
Hmm?
The top bound minus the bottom
That's if it's a single integral. This is a double.
Just the area.
The area of what?
S. D.
It's the area of D. Nobody jokes. Isn't our region of integration rectangular? What is the area? It's 12. There's our surface integral for 24. Wow, it was just so nice. Guess I felt like starting off easy when I wrote these. Surface integral of x squared. So integrate s squared along the surface of the unit sphere. We all knew that the surface of a sphere was going to come up. Parameterization of the unit. Magnitude of the normal vector for the unit sphere. Sine of phi. Double integral over D. Integrand. Evaluated along G. What do you get?
Cosine squared theta is sine squared phi.
Times magnitude of the normal vector, dA. This is what we're integrating. What order do you want to do?
Theta then phi.
Integrate cosine squared of theta from 0 to 2 pi. It's pi. Cosine squared. 1 plus cosine 2 theta all over 2. What's the period of cosine of 2 theta?
Pi.
We're integrating over 2 full periods. So that part goes out to 0. It's just the integral of 1/2 from 0 to 2 pi. Half the length, so you just get pi. Oh boy. This one's actually not that bad. This is doable. What do you want to do?
Change that to sine times sine squared phi,
For what purpose?
so that you can then use the identity sine squared phi equals, and I hope this is the identity, equals 2 sine phi cosine phi equals 2 minus, oh man,
2 sine cosine is sine of 2 phi, not sine squared of phi.
okay, right.
It's a double angle.
Right, then we want to use the identity 1 minus cosine squared phi. No.
Oh, yep, that's the one.
That's the one. All right. Forgot to bring my sheet. Not that I should need it. And then we want to do u substitution with u equals cosine phi.
Then what is du?
Negative sine phi. And
Cosine of 0.
there's 1.
Cosine of pi.
Pi is negative 1.
All right, so integral of 1 from -1 to 1 is just 2. Antiderivative of u squared is what?
U to the third over 3.
What is 1 cubed?
1.
Negative 1 cubed.
Negative 1.
1 minus negative 1.
Positive 1. I mean, 2. Sorry.
It's okay, arithmetic is hard.
It is.
What's 2 minus 2/3?
4/3.
There's your surface integral. Yeah, remember that. Upper hemisphere of radius A, which means we're going to use a parameterization for a sphere of radius A, and then the domain will be restricted because it's an upper hemisphere. There's the parameterization. Given that it's the upper hemisphere, what should our domain be?
Theta goes from 0 to 2 pi. Phi goes from 0 to pi over 2.
There's the norm. Again, that's been derived. So surface integral is going to be the double integral over d. Evaluate z squared along g. What do you get?
A squared cosine squared phi.
Times the norm. When simplified, this is what we're going to have. You should see there's no theta. So when we integrate with respect to theta, we're just going to get 2 pi. How would you do this one?
U substitution.
What's your u?
Cosine squared phi.
And so you're left with negative 2 pi a to the 4th over 3 cosine cubed. Cosine of pi over 2. Cosine of 0 cubed. 2/3 pi a to the 4th. Oh, by the way, I didn't mention it. Surface area. Just the surface integral of ds. Right, it's just the integral over s ds. That's the surface area. Parameterize the surface. Well, it's the part of the surface of the sphere above a cone. So we're just going to use the parameterization for the sphere of radius 2. Right, because that's the surface we're looking at. now for the domain.
Theta is 0 to pi, and phi is 0 pi.
If phi was 0 to pi, that'd be the entire sphere.
So 0
Clearly it's not.
0 to
How'd you get it?
Just seems most logical.
Oh dear. Why is it the most logical?
It has to be above, and then like the quadrants on only two the cone.
It is pi over 4, but your reasoning is wrong.
So that's where they intersect, right?
0 to something because we're lying above the cone.
Yeah.
So it's clearly going to be starting at the z-axis and then coming down. Something comes down to where the two surfaces intersect. Well, if z is the square root of x squared plus y squared, that means x squared plus y squared is z squared. 2z squared is 4, z squared is 2. Which means z is root 2 because z has to be positive. But what's z? 2 cosine of phi. Right, because we're in spherical coordinates. That means cosine of phi is root 2 over 2. What's phi? Pi over 4. Norm is 4 sine of phi. Radius squared times sine phi. So evaluate the integrand along G. What do you get?
sine theta sine phi cosine phi.
Times
4 sine phi.
simplify. Sixteen times the double integral sine theta sine squared phi cosine phi. You have 3 seconds. What's that integral? Oh dear.
Do all those guys.
0. What's the period of sine?
2 pi.
Oh, we're integrating sine of theta over 0 to 2 pi. That whole thing is 0. That is schmexy.
Still not used to that.
Huh?
Still not used to saying that.
Well, that is schmexy. Look at it. Sexy ass equation. Love it when it just goes to 0. Hate it when I spend 5 hours only for it to go to 0. Oh, Miss Physics, you're going to be dealing with that a lot. She's not even paying attention. Throw something at her. She's still not paying attention. Could have hit her with like $18 and she wouldn't have noticed. Miss Physics. Get used to doing 5-hour problems to get 0.
Oh, well, I get so pissed off when I deal with that.
That happens a lot in physics.
It's really infuriating.
Yeah, it is. But it's also nice because you want most things to be 0.
That's true.
It's even more infuriating when you spend 5 hours and you get infinity. Because then you know you screwed up. And you're like, oh shit, now I gotta figure out what I did wrong.
And where exactly all of this did it go
When
wrong?
things go to infinity, we know we screwed up.
It's real bad.
When things go to 0, we know we did it right. Okay. Well, that's enough of that. Now we got to do flux. Do we have to? Yes, sadly.
I was in the bathroom for about 5 minutes. Do you have to do a lot of proofs?
In what, physics?
No, that's fine.
We have to do a lot of proofs? No, but in physics you do. And they're awful. So our surface is the surface of the part of the plane 2x plus 3y plus 6z equals 12 that is located in the first octant. Can we write the plane as z equals a function of x and y?
Yes.
Then there's our parameterization. What is z?
12 minus 2x minus 3y all over 6.
Simplify it. Well, I guess that technically simplified. Split it.
Can't do this in my head.
Can't.
Well, when you start splitting fractions up, well, maybe
You should take the 1/3 out.
What's 12 over 6?
2.
What's 2 over 6?
2 over 6 is a third.
3 over 6. See? You can do that in your head. There's a reason I wrote it that way. You need a domain.
X goes from 0 to 6, and then y from 0 to 4.
If you plot it out, your domain is actually a triangular region. So y is going to depend on x.
How would you find that out if you didn't plot it?
Set z equal to 0. Two x plus 3y equals 12. Then you solve for either x or y.
Oh, okay.
In this case, I solve for y. Now we need the normal vector. This is where orientation matters. You have two orientations, outward pointing and inward pointing. Right, it means either normal vectors point out of the surface or into the surface. It's not mentioned here, which means we, by default, assume outward. That is considered to be the positive orientation. Just like counterclockwise is positive orientation, outward pointing would be positive orientation. So we're going to use outward pointing normal vectors. That's important to keep in mind. N. Right, is technically g sub x cross g sub y, or g sub y cross g sub x. You don't know which one until you calculate them. But they only differ by a negative, right? So you calculate g sub x cross g sub y, and then look at the resulting vector. Does it point in your desired direction? If it does, good. If it doesn't, multiply by -1. Now this has already been derived. What is the partial of g with respect to, not g, I'm sorry, little g of x, y, so z. Partial of z with respect to x. That's why I wrote it this way.
One, zero, minus the third.
I just want z. So just the z component. Right, because what you're doing is you take the partial derivative of your g, your little g function, g of x, y.
Okay. So minus the third.
Negative of that.
Positive.
Now do it with respect to y.
Half.
Right, it's going to be negative 1/2 multiplied by negative, comma 1.
Why is it negative? Because it's not pointing in the right direction.
No, because that's how it just winds up.
That's
Again, I derived it in the video. That's how it happens. Right, and then you just want to take a look at the result and you go, does that point in the right direction? So does that point out of our surface? Yes, it does. So we're good. That is our normal vector. Flux is therefore double integral over our domain. Evaluate the force field along G. What do you get?
36 minus 6x minus 9y, comma,
All right, now, what do you guys, the second component? Oh, this one's really hard.
minus 12.
And final.
3y.
All those are nice. Dotted with N. DA. So this is where, before I even calculate this, flux can be positive, negative, or zero. So it's representing a net flow. What would a positive flux mean?
That there's more movement. You said flux it.
So the correct answer is it depends on the orientation. So we're going to assume outward pointing. A positive flux means net, you have more flow out of the surface than into the surface. Negative would mean you would have more flow net into the surface than coming out of the surface. Well, then that means that zero would mean they cancel out. Right? You have equal flow in and out, which is desirable in most cases.
0.
That would be zero flux. Right? The amount of field flowing into the surface is the same as the amount that's coming out of the surface. That's really ideal. Perform that dot product.
Six minus 2x.
That is what you're going to be left with when you do the dot product. Yes, 6 minus 2x. We don't have a choice on the order of integration. Give myself more room so we can all see the bounds. It was 4 minus 2/3 x. I'm actually going to factor out of 2, I think. Make it a little bit easier. Why did I do dA? Because I'm silly. dy dx. Integral with respect to y is what?
4 minus 2x over 3 times 3 minus x.
Yeah, I don't care about that. 3 minus x. With respect to y, it's just that 4 minus 2x over 3, right? And then multiply by. And how'd you get that so quickly?
Just the way.
There is no y. That's nice. We love integrals like that. Factor out of 2/3. Four divided by 2 times 3. Right, so 4 times 3/2 is what?
6.
That couldn't have been 3 minus x. No, it had to be 6 minus x. We don't have a choice, we have to FOIL that. (18 minus 9x plus x squared). What's 18 times 6?
108.
6 squared
36.
over 2
18.
times 9.
162.
6 cubed
216.
over 3.
72.
Another way you could have done it, 6 cubed is 3 cubed times 2 cubed. Over 3, you get 3 squared times 2 cubed. 9 times 8, 72. What's that sum? 18 divided by 3 is 6 times 4. There's our flux. 24. Flux of that force field through the surface of the cylinder, x squared plus y squared equals 16, located in the first octant between 0 and 5 for Z. So first we need a parameterization for the cylinder. Again, this was given in the lecture video. For extending along the z-axis, radius times cosine, radius times sine, and then z. What would the domain be? Half the domain is easy.
X would be,
X.
oh, beta and Z. Would be between 0 and 5 for beta.
You said that?
between 0 and pi over 2.
Why?
Because it's in the first octave.
Oh, first off, I see that.
This is n. Does that point in the right direction? So is it pointing away from the surface?
Yes.
Yes. That's the one we want. Evaluate the field along G.
Z for cosine phi or theta minus 40 sine squared phi z. I keep saying phi theta.
That gets dotted with our n. Oh, that is sexy. What is that dot product?
Four z cosine theta plus 4 sine theta cosine theta. Oh yeah, 60.
Simplify it. Double angle. Identity for sine. Again, there's a reason why I did that. Actually, it's not 0 to 2 pi, is it? So that's not going to work. 0 to pi over 2, 0 to pi. Theta. Sine 2 theta. Easy theta, let's do. Integrate with respect to z.
50 cosine theta plus 40 sine 2 theta.
What was it?
50
50, okay.
cosine theta, and that one's plus 40 sine 2 theta.
Factor out a 10, which I'm going to do to make life easier. What is the antiderivative cosine?
Negative sign.
Antiderivative sine of 2 theta.
Negative half cosine 2 theta.
Which means one of these should not be negative. They're not both negative.
No, yeah, the first one is not negative.
So then that'd be minus 2 cosine of 2 theta. Sine of pi over 2.
1,
Sine of 0.
0.
Cosine of 2 times pi over 2.
Negative 1.
Cosine of 2 times 0.
1.
So that's negative 2. We get a flux of 70. Uh-oh. That is not. There we go. It's possible that this I just did wrong.
Because you evaluate your top domain, I would assume that's what you get, but then when you put in theta is equal to 0, then you'll have minus something.
No, 0 is positive 1. So it'd be negative 1 minus 1, which is negative 2. Times negative 2. I'm an idiot. Should be plus 4. That's what it should be. 90. I want to make sure I have time, so I'm skipping that one. Coming to this one. Evaluate flux through the surface of the unit cube. What do we think the unit cube is?
A cube where the length of each edge is 1.
And it doesn't matter where we orient it. So let's orient it where one of the vertices is the origin. That just makes it easier. Is the unit cube a closed surface?
Yes.
It is. Oh joy. So by the way, in that case, we could write this. But I'm not going to write the rest of it. Right, so just like circulation, right, you had a single line integral the circle, that meant that the path was closed. Symbol like this means that your surface is closed.
Is the unit sphere a closed surface?
Okay. But we never actually considered the entire unit sphere, I don't believe, did we?
We did once.
That was for scalar, right?
I think so.
Yeah, that's why we don't typically use this notation for scalars.
Okay.
Only for fields. I guess you theoretically could. I don't see why you wouldn't be able to represent it being closed. We just don't. I wish I had a cube. So I don't have a cube.
Not that I know of.
Nobody here has like a Rubik's Cube of some sort?
I don't carry dice on me.
No.
Not everywhere.
You've disappointed me. Do I have anything that's cube like that? This will work. We're just gonna pretend that this is a cube.
Just cut it. Grab the scissors or something.
It's not mine. We'll just pretend that this is a cube. It's cube-esque.
It's a cuboid.
It's a right. A cube is a special type of this, right? It's a rectangular. That's still holds. Closed surface. So we would have bottom surface, right? Top surface. For you, front surface, back surface, left surface, right surface. We have 6 freaking surface integrals we have to evaluate and sum them up. I'm surprised you didn't say anything because I mentioned that to you on Tuesday. Right? Was that the last problem we did or the first problem with circulation? Oh, no, I don't think it was circulation, was it? It was a scalar, but it was a closed square, wasn't it? Or a rectangular something. I forget when we did it, but we definitely did it.
Yeah, that was a rectangle.
It was a rectangle, wasn't square? Well, square is a
Yeah,
rectangle.
it was a square.
And we had the 4 paths, right? That squares the union of 4 non-overlapping paths. Well, a cube is the union of 6 non-overlapping surfaces. Since it is indeed a closed surface, we have to deal with all 6 of them. The general theorem still holds. Right? If your total surface is the union of non-overlapping surface, then your surface integral is the sum of each individual surface integral. So the flux would be the sum of the flux through each individual surface. Look like a square?
Yeah.
About.
Good enough for government work. So it looked like they had the same length.
I think they're a little off.
Yeah, good enough for government work.
You completely blew it.
That is
Yeah.
not good enough for government.
Actually, yes, it is. I don't think you underestimate the power of government screwing things up.
That's true, actually.
If you need proof, what's our national debt? I rest my case.
Honestly, you could have said any number of things, and the argument still would have held. There were so many options you had.
Could have said military grade. squares go safer. Music breaks.
What are the 9 most terrifying words?
Oh, I'm from the government and I'm here to help.
From
Is
the
that what
government,
it
I'm
is?
here to help.
Was it Reagan who said that?
Yes.
That's a quote.
Possibly the best quote ever. You know, I don't care. That's going to have to do. That cube is too good for government work.
Now we gotta do it again and we'll time you.
You can go jump in a pit of hungry vipers.
At least it's not infinite.
You wish it was.
Alright, you know what? Well, then the Vipers would still be there.
Oh, maybe I'll do worse. A pit full of angry yellow jackets.
Oh, that would suck.
What about murder hornets?
Human size potential harmfuls.
Human size.
Well, first off, a human-sized shrimp. No, that's just a flamethrower. Maybe even a flamethrower is not enough. Maybe a freaking bazooka. Napalm, a nuke.
It's like those
And
ants
you know
that
what
are
I'm
able
talking
to
about?
Going up on one of Elon Musk's rockets and shooting a laser to blow up the Earth. Damn that. I was gonna say, or maybe a pit of fire ants.
The fire ants would be fun. Just
I don't think that would kill you either. It would just be very uncomfortable.
What?
If it does kill you, it would kill you much slower than angry yellow jackets.
The worst part
Pit
is
filled with
that-
awkward social situation. You'd be very uncomfortable, but you'll still be fine.
No, I don't know that fine. I've ever been attacked by a swarm of fire ants.
No, I said awkward social situations.
You're too shy to ask someone to move out of your way, so you kind of just.
I'm going to designate this vertex as the origin. Because remember, positive x comes out at you. That's why that is serving as the origin. Use very common notation. A circle dot, when talking about arrows, represents an arrow coming out. So that's going to represent the front facing. You need a parameterization for it.
X is equal to 1.
Y comma Z.
What's the domain?
X is 1.
True, or that y and z. Because remember, this is a parameterization of y and z. It's two variant.
From 0 to 1.
And again, that's very common notation to represent that. What's the normal vector? Was it?
100.
100.
Because of the out best value being outward.
Right, so again, think of this. That'd be a vector, right? Point strictly in the x direction.
And it only goes to 1 because it's
Right, so a circle with an X, when talking about arrows, would refer to into the page, so going away from you. It gets really confusing when you study more advanced math because there are circle dot and circle cross operations. Oh, and also the circle dot also represents the sun.
Oh, yeah. So
It's the astrological symbol for the sun. Was its parameterization. By the way, do you know the sun's name?
Sol.
You know the moon's name?
You know the Earth's name? Other than Earth? Terra.
There, yeah. Which is why we don't capitalize sun,
Yeah, because it's just a sun.
but we would capitalize sol because it's its name. I think if you say the sun, then sun gets capitalized.
Yeah, that makes sense.
Same thing with Earth. Earth isn't capitalized if you say it's the Earth, then it's capitalized. But Terra would be.
Should that be -1 YC?
And by the way, you disappointed me by not knowing that.
Kind of guess. I'm getting there.
What's the domain? Take astrophysics as an elective.
Why is it -1 YZ, not 0 YZ?
Because it's going inward. Instead of going outward for the one, we're going inward. It's the length of that vector.
Okay, I think I'm confused about which of the surfaces we're talking about.
What?
It is 0.
I was so confident. Oh, wait, it's because we're at the origin. We're going back to the origin. Got it. Got it.
Y and Z will still go from 0 to 1. What's the normal vector?
Would it not be negative?
That one's negative I hat.
Okay, it's not 0.
Wouldn't that one also just be positive I hat? No, it is negative I hat.
Right? If it was positive I hat, no, it's be pointing into the surface.
I don't understand what you're doing with red right now.
Here's the front of the cube, here's the back.
Okay.
This is the vector. The tip is the arrow. Positive I hat would be going into the back. You want to flip around to come out of it.
Got it.
Let's do the right surface.
That one would be X. 1Z.
Domain,
X is except for switch out the y for an x. That, yeah.
Normal vector.
0, 1, 0.
Don't give it to me in that form.
J hat.
So look at the left facing. What would it be?
X, 0, Z.
And what is the normal vector?
Negative 11 from 11.
Negative j hat. Top facing.
Y.
Equal to 2x, 0 greater than equal to, well, I'm getting myself on track.
Yeah, X and Y.
Is it greater than or equal to?
It's less than, I'm not having my things. Would it still be 1 or would it still be 0?
Goes from 0 to 1. Because it's the unit cube.
Oh,
And what's the normal vector?
Negative K.
Just k.
Or just K.
Right, it's pointing up.
Right.
What about the bottom facing?
X, Y, 0. X, Y, 0.
And what is the normal vector?
Negative K.
So our total flux is the sum of those 6 fluxes. Very careful when you say flux. Don't say it too fast. Here is where we're going to use a little intuition. What happens when you multiply a vector by I hat or dot product it?
The rest kind of goes away.
Not kind of.
It just doesn't.
Yeah, it's just the first component, isn't it? Evaluate 4xz along the first parameterization. Be 4z, right? Because x is 1. Oops. X is 0. That whole thing's 0. Which means we have no flux through the bottom.
So the second half of each of the negatives facing
I'm gonna-
are gonna all be 0.
Ignore that. All right, so we're not going to write out that one. Now for the right. What happens when you multiply a vector by j hat?
Just the second component.
Right. So this is all we care about. The negative y squared. It's just negative 1. I will keep it as plus. I think I will write this out just to have it. If you look at the left, It's just 0 squared. What happens when you dot product a vector by k hat? So this is the one we care about now. So that's what, just y?
Yes.
And what about the bottom? Oh, this turned out to be so schmexy. 3 of them go away right away. That's so beautiful.
That's good.
0 to 1, integral 0 to 1 of 4z dz dy minus, oh, minus the area of that domain, which is a square, by the way. Plus that. Look how easy this wound up being.
You call that a 0, the lower bound for under that sentence? It's better.
Ever since that cue, no one was digging on this one.
I think I'm going to throw you into the pit of firings.
Pit of indeterminately bad creatures.
You just never get a paper that can squeeze in one of you something.
I'll just call it torture.
He's throwing someone into a pit of fire. It's not.
No.
Oh, okay.
Imagine being hung upside down when they're draining, except instead of using a knife, just paper cuts along the jugular.
Put some hand sanitizer on it.
That is real torture right there. And I let him heal too. And he stuck the itch. This just becomes 4z, right? Which is 2z squared, so that's 2. Minus, what's the area of the square? And then this just becomes y, so y squared over 2 from 0 to 1. What is that?
3x.
And there's our net flux. That could have gone a lot worse. It's just a nice, simple example of showing you 2 things. 1, what a closed flux would look like and how you'd have to break it up into different surfaces. And 2, why I hate flux so much. Questions on flux and surface integrals? We meet one day next week, Tuesday. Tuesday, we start the climax. We look at Green's theorem on Tuesday. Before I let you go, I did promise you something. form of Maxwell's equations. And I did show you differential form already. Most important 4 equations. This is week 12, which means you have your 3rd quiz, and it will also be your last quiz. That will be due by 5 p.m. on November 28th, which is Thanksgiving, so do it before then.
Are there any more discussions for the rest of the semester?
Probably not. Maybe one at the end, maybe. Haven't decided.
Is it like an ambush?
And you also have the 4th project, due November 26th.
An hour, he uses an hour.
I would go on